Hello everyone, thanks for stopping by, and today we're going to be looking at our last notes packet for Math 121, and this section is going to present methods to talk about population proportions. Now, a proportion deals with cases where something either is or is not part of the group you are considering. There's only two outcomes. We typically call those sort of situations binomial for two. Right? Because bi like bicycle. Now, in this section, we're going to have a few different definitions. The first is a point estimate. A point estimate is a single value used to estimate a population parameter. The sample proportion, p with a little arrow over it, which we call p hat, is the best point estimate of the population proportion p, which is the percentage in the population that we have. We're talking about proportions, right? So think about like our first example here. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on that result, find the best point estimate of the proportion of adults who have a Facebook page. We're looking at all adults now, right? So think about this scenario. You're studying a group of individuals, 1,487 of them to be precise, and you ask them, yes or no, do you have a Facebook? And in your group, 43% of them said, yeah, I do. So, with that in mind, what would be the best estimate for all adults? Well, the sample proportion that was given, p hat, was 43%. That was given. We were given that in our sample, 43% of them have a Facebook group or Facebook page. Now, if I had to take a guess at what the overall percentage would be for everybody, it doesn't seem unreasonable to just guess that same number. So, based on these results, the point estimate would be P equals 43%, or 0.43, depending on whether you want percentages or decimals, right? Remember, percentages and decimals are two ways of writing the same concept. Now, is this going to be exactly correct? Most likely not, right? There's probably going to be some room for error, right? We're just assuming it's the same value as our sample, right? Our sample said 43%. We assume the population is also 43%. Now, obviously, there might be error, right? To account for potential error, we have the main idea of this section, which is confidence intervals, sometimes also called interval estimates, but we'll call them confidence intervals for the most part. And a confidence interval is a range of values used to estimate the true value of a population parameter. So we're going to create a range that we think the real answer is going to be in. So our sample said 43%, so maybe we construct a range around that number that might have the real answer in it. We're going to build a boundary, right? We're going to try and zero in on the answer, but we're not going to take an exact guess like we did in this first example. Now, the confidence level is the probability 1 minus alpha. Alpha is a notational value here, such as 95% or 0.95. So we are some level of confident, right? We have some confidence level that the interval actually does contain the population parameter. So we could be, more or less confident depending on what our confidence level is. You can change this values, and we'll see some common examples in a moment. We assume that the estimation process is repeated a large number of times, right? It's always good to repeat studies, right? That way you can draw your results more confidently, right? The more you repeat a study, the more conclusive your results are done. And then we sometimes call the confidence level the degree of confidence or the confidence coefficient. Typically we call it confidence level though, but these words are synonymous with confidence level. Now, the following table shows some of the relationship between confidence levels and the values of alpha, as well as an idea called critical values. So the common confidence levels you might see are 90% confidence, 95% confidence, or 99% confidence. So you're becoming increasingly confident that you have actually found the true value, right? And each of these is going to have a corresponding value of alpha, which here, this alpha is 0.10. It's the opposite of your confidence level. That's what the alpha corresponds to. And then here, your confidence, your value for alpha at 95% confidence would be 0.05. And then for 99% confidence would be 0.01, right? The alpha value decreases as the confidence level increases. They're inversely related, right? Now, what are critical values? Critical values are values we will actually be using in our formulas. And the good news about critical values is for these common confidence levels, you don't have to do any work to find them. Normally, you would have to use this z-score table to find your appropriate critical values. However, the table already does the work for you. Notice it says common critical values down here in the bottom right corner, and then it says confidence level and critical value. And then it has 0.90, 0.95, and 0.99. Those are the same three as right here. These are the only three levels of confidence we will deal with. You can deal with any level of confidence. You could be, 50% confident, 99.9999% confident, 72% confident, any number you want, right? But these are the three we will be dealing with. And the critical values from the table, well, first is 1.645. The next is 1.96. And the last is 2.575. These are the critical values we will use. And the symbol for critical values is a z, because they're related to z-scores, and then an alpha over 2, because it relates to this value of alpha. And if you're interested in seeing how these are calculated, for other numbers, besides the ones we're going to be using, this is in section 7.1 of the book. However, we're only going to be using these specific critical values from the table, right? The ones the table has already calculated for us. But like I said, you could use any confidence level. So that's an introduction to the ideas we're going to be dealing with. Now, on the next page, let's take a look at how we would interpret some of these results. We must be careful to interpret confidence intervals correctly. There's a correct interpretation and many different and creative incorrect interpretations. Here is a confidence interval. The interval says P, the value we're looking for, is sandwiched between 0.405 and 0.455. That is the confidence interval we are constructing. Now, if this was at the 95% confidence level, a correct interpretation of this inequality here, this sandwich with the population proportion in the middle, could be we are 95% confident that the interval from 0.405 to 0.455, right? These are my bounds of my interval. We are 95% confident the interval from 0.405 to 0.555, or 0.455, sorry, does contain the true value of P. And P will be whatever you happen to be studying, right? It'll be related to what you're studying. So we can interpret these intervals. Be careful, though. Don't use the word chance. Chance is incorrect. Chance relates to probability. We're talking about confidence level. We want to use the word confident. So we'll say there's a 95% chance the true value of P falls between those two bounds. That is incorrect. We're not talking about probability. We're talking about confidence. How confident are we the answer's actually there? And then another wrong interpretation might be a little more creative. We're getting a little more creative with the language, but it still isn't quite correct. It says 95% of sample proportions fall between 0.405 and 0.455. That's not correct either because it doesn't mention confidence. Once again, we're talking about confidence intervals. We need to make sure we mention that it's confidence, right? That's the key concept here, is we're building confidence intervals. We're not talking about probability or chances, and we want to be careful of those pitfalls. So make sure you're aware that the correct interpretations involve the idea of confidence. Now, how do we construct these intervals? Earlier I mentioned on the first page, when we talked about the point estimate, there might be some error associated with that guess, right? This is what my sample told me, and I guessed that my population had that same value. But there might be error, and that's what this next section talks about. When data from a simple random sample is used to estimate a population proportion P, so we're estimating the proportion, the difference between the sample proportion and the population proportion is an error, right? There's likely to be some error between your sample value and your population value, right? That's just how grouping works, right? If you take a group of people, they're not likely going to have exactly the same values as the whole population does. It'll probably be close, but there might be a little bit of error. The maximum amount of error is the margin of error. And we use the letter E for the margin of error. We use the letter E. Now, we can say there's a probability of 1 minus alpha that the difference between P hat and P is E or less, right? That's what our confidence level lets us know, is how likely our answer actually falls within the interval we are looking at. That is what our answer can show us. So we're looking at a sample, and we're estimating the population. We're drawing conclusions about our population based on our sample. Sometimes the margin of error might be called the maximum error of the estimate, and it can be found by multiplying the critical value and the estimated standard deviation of sample proportions. We'll look at this formula right here. The formula for E is equal to the first value in the formula is that Z alpha over 2, the critical value. Those numbers from the first page or from the bottom right of your table. That's where you get your critical values, your Z alpha over 2s. Now, what's the remainder of the formula? Well, after that, we take a big square root, and in the square root we have P hat, we have a symbol known as Q hat, and we have an N in the bottom. And this bit of a big formula, right? It's got a little bit going on. This formula will give us our margin of error. Now, we need to know what all these symbols mean. So let's look at some notation. The population proportion, that's the value of the population. How many people in your population, what percentage have the desired characteristic? In the earlier example, it was how many people have a Facebook. What percentage, right? That symbol is plain old P. That's the population proportion. The sample proportion is P hat. The sample proportion is P hat. That's the percentage or the proportion of people within your sample that have the desired characteristic. Now, Q hat is the complement. It's 1 minus P hat. It's just the opposite group. This is the group that does not have the desired characteristic. So with the Facebook example, P hat is the percentage that did have Facebook, and Q hat would be the percentage that did not have Facebook. And those are related ideas, right? P hat and Q hat. That's why they appear next to each other in the formula. They're complements of each other. Together, P hat and Q hat make up the whole group. Because, remember, these are binomial. There's only two outcomes. Either you do or do not have Facebook, as the example we used, right? Maybe another example, maybe you do or do not have a brother, right? You could ask people that question. Do you have a brother? Yes or no, right? These are yay or nay type situations. There's only two outcomes. They're proportions. Only two outcomes. You either are in the group or are not in the group. Now, the number of sample values, that's n, right? N is the number of sample values. That's always been true, right? That's not a new symbol. The margin of error is the E, and then the critical value is the Z alpha over 2. That's whatever number you need from this table, right? That's whatever number you need from that table. And that is the notation that is used in the error formula, right? Critical value, sample proportion, the complement of the sample proportion, and the size of your sample. And those are the numbers you need to calculate the error. Now, let's look at how do you construct a confidence interval. What are the requirements and what's the procedure? Well, first, the requirements, there's 3 of them. The first is it has to be a random sample, right? You have to have a random sample. You can't have any other type of sample. Second, it has to be binomial. There has to be only 2 outcomes, yay or nay. It can't be more than 2 outcomes. If your question has more than 2 outcomes, you cannot construct a confidence interval in this way. It has to have only 2 outcomes, yes or no. You have a Facebook, you don't have a Facebook. You have a brother, you don't have a brother. Yes or no questions, right? You have a wallet in your pocket, you don't have a wallet in your pocket, right? It has to be yes or no questions. And then the third is there's at least 5 successes and 5 failures. At least 5 members of your sample must be in the group, and at least 5 members of your sample must be outside of the group. So you need to have both cases. If you ask a group of 100 people, do you have a Facebook? And 97 of them say yes, and 3 of them say no, that fails to meet the 5 requirement, right? You have to have 5 in each group. So maybe you get a larger sample, right, to find more no's. You need at least 5 successes and 5 failures. If that's true, if these requirements are all true, then the confidence interval can be calculated. The first value is p hat minus e. That's the first number you calculate. P is the number we're sandwiching. We don't know what it is, so we leave it as the symbol P. The upper bound is p hat plus e. So you're sandwiching the answer you're potentially looking for in between a lower and an upper bound. And here, e is that z alpha over 2 square root of p hat q hat over n. It's the error formula, right? So this error formula is key to solving these questions. The question will give you the p hat, right? You can find the p hat value. The question will give you that information. The e value is what we need to calculate. You also might see these notations, p hat plus or minus e, or parentheses p hat minus e, p hat plus e. They're just different notations that some people use for confidence intervals. I prefer the inequality version. Typically speaking, social sciences prefer the plus or minus version, and then the calculuses prefer this version. This is the preferred version for calculus-based statistics, which we won't be dealing with calculus, but it's always good to know that there are other formats. So that's the requirements. Finally, you round the limits to 3 decimal places, 3 significant digits. We round these values to 3 values. We want 3 significant digits, right? We round to 3. Remember, z-scores are 2 decimals. Here we're rounding to 3. Our answer will be rounded to 3, right? So, if these are the requirements, what procedure would we follow? Well, step 1, verify you've met the requirements. Step 2, find the critical value, which, remember, comes from the bottom right of your table. It'll depend on what level of confidence you want. Step 3, calculate E. Step 4, using E and the sample proportion p hat, you create the limits. You create the lower and the upper bound. And then you round and you're set. You have your answer. Those are the steps. Requirements, look up the critical value, calculate E, construct your limits, and then round and set them up. Those are the 5 steps to creating a confidence interval. And it's always those 5 steps. So let's take a look here at an example. Now, we noted earlier that a Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook pages. Now, I have shown that that means N is 1487. That's how many people I sampled, right? And P hat, the proportion of people in my sample, was 43%, which is 0.43, right? These two numbers might not be given to you. You might have to interpret them from the sentence, right? But here they were given to you. They are also given right here, right? These are the same. This is the same information, right? Those things I boxed are all the same information, right? It's just how does it look on the paper? So, what are we doing? Step 1, find the margin of error that corresponds to a 95% confidence level. So for step 1, I want to find E. I want to find what is E equal to. Well, remember, the formula for E is Z alpha over 2, big square root, P hat, Q hat over N. Now, we need to know what these 4 numbers in the parentheses are. Right, in the formula. We need to know what Z alpha over 2 is. We need to know what P hat is. We need to know what Q hat is. And we need to know what N is. We need to know those 4 values before we can calculate the error. Now, P hat was given to us. It's 43%. But remember, you got to use a decimal for formulas, right? You can't plug in percentages. You have to use the decimal. So P hat was 0.43 because it corresponds to the percentage in the sample that had my desired result. 43% of them, or 0.43. That's the proportion I'm looking for. Now, N was also given to us. We know there was 1487 total adults. 1, 4, 8, 7. We know that that is how many people were in our sample. Now, Q hat. Remember, Q hat is the complement of P hat. It's 1 minus P hat. It's the opposite. It's the people who did not have Facebook. The people that did not have Facebook. So 1 minus 0.43, which gives us 0.57, right? If 43% did, then 57% didn't, right? These values should always add up to 1. They make up the whole. There's only 2 options. You either did or did not have Facebook. No other alternatives. Only those 2. So those are the 2 values that correspond to did have Facebook, did not have Facebook. Now, that only leaves us 1 value left to calculate, or to find, and that's the Z alpha over 2. Lucky for us, the question says we're at the 95% confidence level, which, remember, on the first page, we said the critical value for the 95% confidence level is 1.96. You can also find it on your table here, 1.96, right? 1.96 is our critical value. So let's write 1.96. So now I'm going to plug these numbers into my formula. Now be careful. When you're plugging in, make sure that you plug in neatly. This formula has a lot going on in it, and you want to make sure you can read what is going on. Over 1487. Now, calculating this value, calculating E, be careful of the order of operations. In the numerator, inside the square root, is p hat times q hat. You have to multiply these two numbers first. 0.43 times 0.57. I multiply those two numbers first. Then I would divide by the 1487. Right? Then I would divide by 1487, which gives me a value. Now, that value is the number inside the square root, right? I multiplied and divided. So next, I take the square root. So I square root that number. Finally, I have everything in the square root figured out, and I've taken the square root. The last thing you do is multiply by the critical value out front. That's the last number you will use. You do numerator, then you divide, then you square root, then you multiply by the critical value. So we'll do times 1.96, which gives me an E value, an error value of 0.0251613. Do not round your error. You do not round this number. Do not round your error. Keep all of the decimal places you calculate, because we round at the end. So our margin of error is this. Now, if the program tells you to round to like 5 decimal places, you would round as it tells you, right? But when you're working on your paper, if it doesn't tell you to round here, don't round. You won't round until you get to the confidence interval part, till we get to part 2. So part 1, we calculated the error, right? We calculated our error. Part 2, we want to construct the confidence interval. So for part 2, we are looking to calculate what p hat minus E is equal to, and what p hat plus E is equal to. We want to compute these two values. Now, we already have all this information. P hat was 0.43. Minus E is 0.0251613. And then P hat plus E would be 0.43 plus that same number, right? You add the error and you subtract the error from the P hat. Remember, this is the sample proportion. This is how many people in our sample had the property. 43% of them, right? 43%, 0.43. Now, first, here, we get 0.4048387, which now we round. We're creating the limits. This is the lower limit. I round it to 3 places. 0.405. 0.405. And then I calculate the upper limit. So I take my margin of error and I add 0.43. I get 0.025. 4551613, which now I round to 3 decimals, 0.455. 0.455. Now, I have my lower and upper bounds. I am ready to create my confidence interval. Let's write the answer. Let's write the confidence interval. The confidence interval is 0.405 is less than P is less than 0.455. Or, if you prefer percentages, you could also write them as percentages. 40.5% is less than P is less than 45.5%. So these could be my confidence intervals. What this is telling me is the actual percentage of all adults is between these two values who have Facebook, right? Of all adults who have Facebook, I think the answer is between these two bounds, lower bound, upper bound. I don't know where in the bound, where it falls in between these two numbers, but I think it is between those values. Now, how would we interpret this? That's what part 3 is asking. It says, based on the results, can we safely assume that fewer than 50% of adults have Facebook? I'd say so, yeah. Look, I think the answer is between these two numbers, which is fewer than 50%, right? But how would we phrase that? Let's assume we're a newspaper reporter. Write a brief statement that accurately describes the results and includes all of the relevant information. So here we're going to interpret what we just did. This is where we understand and draw our conclusion. This is where we interpret our calculation, right? All we've done is calculate. Now we're going to understand. So for part 3, a potential answer for this sort of question could say, based on a recent Gallup poll of 1,487 adults, we are 95% confident. Make sure you mention the confidence level, right? 95% confident. We are 95% confident that the true proportion of adults who have Facebook, I'm going to abbreviate it FB. We are 95% confident that the true proportion of adults who have Facebook is between 0.405 and 0.455. Or you could use the percentages if it was appropriate, right? I generally prefer decimals because you can use them in calculations, but percentages sometimes are easier to understand. So this sentence interprets what we just calculated. We're 95% confident that the true proportion of adults who have Facebook is between these two bounds, right? These two bounds. We don't know where in those bounds, but we're 95% confident it lies somewhere within those bounds. Could it be outside of it? Yeah, we're 5% confident it's not within those bounds, right? But being 95% confident is being pretty sure of yourself. You can never, and I repeat, never, in statistics, be 100% confident. You can't construct a 100% confidence interval. You can only go close, like 99 or 99.9 or 99.99%, right? You can't have 100% because you wouldn't be able to calculate the interval. Because if the only interval that you're 100% confident contains it is the interval 0 to 100, right? The whole possible spectrum, right? Either 0% or 100% of them are true, right? And that isn't helpful, right? That's not revealing. That's not a real confidence interval. So keep that in mind, that confidence level can't be 100%. You don't get meaningful results that way. You have to have some level of confidence. Usually 95% is the standard. That's what most studies stick to. In medical sciences, they might use 99% since, in medical studies, lives might be in the balance, right? If you're studying diseases or viruses or medical treatments, you want to be a little more sure of yourself than about Facebook, right? This is a little lower stakes, so we can maybe use 95% instead of 99%. And that is an example of how you would construct a confidence interval, right? The first thing we did was calculate our error. Then we constructed our bounds. We created our interval. And we interpreted what we calculated. And that is how confidence intervals are used. It allows you to take the sample results, right? I only asked 1,487 people about Facebook. But in the end, I can make a conclusion about the whole population of adults. And that's what statistics in the long term is about. You take samples, and then you draw conclusions about the population, right? You take a smaller sample out of your population and extrapolate the results to cover the whole population, right? That's what we did here, right? We just took a small sample, right? 1,487 adults. We didn't ask every adult, but we were able to draw conclusions about every adult. And that brings us to the end of our confidence interval section. Hopefully you've enjoyed this section, and I wanted to take a brief moment now to thank each of you for a lovely semester. I know that remote learning has been a little bit different for us than maybe a traditional classroom, but I've enjoyed my time working with each of you throughout the course of statistics. I hope you have enjoyed the course as well, and I'm excited to enter these last few weeks when we talk about finals and we have our last few meetings and we get ready for that summer break, right? I hope you've had a good semester, and I will see you next time.